In the final subsection of this lecture, we'll see how to approach multi-step synthesis in a rational fashion. You'll often see this term associated with another, and that is that of retrosynthetic analysis. Which allows us to analyze in a rational way a synthetic target and figure out the best way to make such a target. We're going to illustrate this on an example of a molecule. It's a relatively complex molecule containing both an alkene and an alkyne in this setup. And we're asked to prepare this from the following starting material: benzyl bromide, cyclopentylaldehyde, and acetylene. Now, this is a relatively complex problem, and trying just random things will not work, and will probably get you even further away from the solution than you would have been otherwise. So, to look at this, we need to analyze our molecule thinking backwards and seeing which immediate precursor could we make this from. If we look at this molecule, we'll see that this is an alkyne as well as an alkene. And we could make alkynes in a couple of ways, but we know more ways to make alkenes. And one of the easiest ones would be to make it from an alcohol. So we could have an alcohol that looks like this, and upon elimination will give us a desired alkene exclusively. Now this arrow is the so-called retrosynthetic arrow, because it doesn't indicate an actual synthetic step. In fact, it indicates a thinking process which takes us from our product to our starting material that will give us that step. And then we keep doing this. So now we're asking, how would we make this alcohol? Well, we know a reaction that makes an alcohol and at the same time attaches this alkynyl group onto it. This will be addition of acetylide onto an aldehyde. This aldehyde is already one of our starting materials, so that's been accounted for, while this acetylide, of course, is made from the corresponding alkyne, and the corresponding alkyne, again, is made from an acetylide and a tertiary. And so now we reach all of our starting materials in the way we planned. And this allows us to sort of disconnect our product into precursors that step by step will lead to its formation. Once we have this retrosynthetic pathway outlined, we need to come up with an actual synthetic pathway. So now we need to inverse the direction of our thinking and start thinking about synthesis. And so we'll start with an alkyne, deprotonate it, and then use that to attack our benzyl bromide and to get our first precursor through an SN2 reaction. Again, in these reactions the mechanisms are not required, but you need to know the mechanisms to propose reasonable things. The second step is that now we deprotonate this acetylide and expose it to a solution of this aldehyde, which will result in an alcohol, which is one of our intermediates. Finally, heating this alcohol in the presence of acid will lead to elimination and give us our desired alkene. Now, this is not the only way that this product could have been approached. Alternatively, and this is just one of many alternatives, there are a lot of reasonable alternatives for each of these problems, and there are quite a few unreasonable alternatives. But the alternative in this case will be that we don't disconnect at the first position of an alkene, but instead here. And so we decide to form this alkyne by reacting this acetylide with one of our starting materials. This one. This is already one of our starting materials. How do we get to this? Well, we make this from an acetylene, and an acetylene in turn is made from an alcohol, and this alcohol is reacted by direct attack of acetylide onto the cyclopentylaldehyde. In reverse direction, so in the synthetic direction, again we would start with deprotonation of acetylene, but now in the first step we would react it with our aldehyde to give us the alcohol. Dehydration of this alcohol will give us the alkene, which can then be deprotonated again and then treated with benzyl bromide to give us the final product that we desire. Much of the further synthetic problems in this course will deal really with this. At this point we already have a relatively large arsenal of reactions, and combining them in the most efficient, quickest fashion, and also in a fashion which prevents their contradiction is an important facet. And retrosynthetic analysis is all about that. Thinking backwards from your product to your starting material, proposing reasonable routes, establishing multiple alternatives and weighing those alternatives against each other, and finally, once we pick the best alternative, proposing the reverse synthetic route which will actually provide us with. This is all for today, and in the next lecture we'll start talking about a brand new class of compounds, namely alcohols. Thank you.